Next paper is on forest composition assessment from high-resolution remotely sensed imagery, and our presenter is Abishek.
Hello. Just to ask, how this slide move forward? Sorry.
You can say next, and then our student assistant will move his slides.
So I cannot control from here, right?
No, I believe you can't.
Okay, thank you. Okay.
Yeah,
Hello,
or
and
if you want, you can share your slide on your own screen and then control it.
I think
Would
it's
that be
okay.
better?
I think it's fine. I think it's
Okay,
fine.
sounds good.
Okay, I'm ready.
Okay, so if you want to present the slide.
I got it.
Can you all hear me?
Yes.
Okay, thank you. Hello and good afternoon here from Syracuse, New York. I'm Abishek Patel, PhD candidate in Department of Sustainable Resource Management at SUNY College of Environment Science and Forestry. Today I am presenting a study entitled Forest Composition Assessment from High Resolution Remotely Sensed Imagery. So this work was, yeah, it's okay. So this work was an alternative to perform study remotely in case there would be uncertainties or restriction on travel to study sites for field work due to COVID. So it was part of 2021 summer work for me. So initially I was supposed to fly drone in the study sites to acquire very high resolution imagery on varying forest vegetation in Adirondack, New York. So this is my first time presenting this study among the peers, and I did get feedback from AutoCarto 2022 abstract reviewers. So I tried to incorporate those suggestions and present my initial methods and approach adapted to classify forest composition and detect, delineate, and estimate individual tree height. Can we go to the next slide, please? So here is my introduction, starting with the introduction, material methods, and then results, discussion, conclusions, and then conclude it with acknowledgements and questions and queries. Next slide. So vegetation assessment. So forest inventories and monitoring activities are very critical to sustainable forest management. One critical element of this type of monitoring program is assessing for vegetation. The primary purpose of vegetation assessment is to determine current stocking levels, potential future stand density, and spatial arrangement of the desired forest stand. Timely and accurate vegetation assessment is also critical for landowners to determine if current stocking levels are adequate to meet future management objectives and to make proper decisions related to the future management activities. Can we go to next slide, please? Airborne and satellite data has been integrated in field-based forest assessment and are widely used in mapping forest composition and attributes from regional to global level. Traditionally, remotely sensed satellite, airborne, or active data products has been used for many forestry applications, including forest monitoring. However, these data sets are constrained by cost, resolution time, and weather. It isn't easy to detect young trees or look into recently harvested areas and utilizing low resolution remotely sensed data products. So evaluating new methods or methodologies to improve monitoring efficiency is critical and essential. So combining open source, open multi-source remotely sensed data can help in collecting forest attributes and high spatial resolution and get high spatial and temporal resolution datasets. Additionally, these datasets improves species identifications and maximize individual tree detections, measurements of canopy gaps, and species classifications. Next slide, please. This study involves a suite of remote sensing data to estimate, classify, compare, and visualize spatial patterns of vegetation in study sites managed by Molpos Woodlands Group in Adirondack, New York. Remotely sensed data used for this study were combining three different sources: USDA, National Agriculture Imagery Program, or NAP, and another one is New York State GIS Clearinghouse orthoimagery and LiDAR data to quantify and classify forest vegetation. Leaf on or off imagery data collected from USDA, NAP, and New York State orthoimagery online sources are used to separate and classify conifer and hardwood species. LiDAR point cloud data is used to quantify vertical structure and to assist in creating a canopy height model and further classifying individual tree segmentation. Even though NAP and New York GIS Clearinghouse orthoimagery data are of slightly lower resolution compared to data acquired from UAV or drone, it does provide sufficient information to quantify and understand spatial patterns in vegetation. This will enable us to compare the cost efficiency and effectiveness of using multi-open source remotely sensed data sets with high resolution UAV data products in future. So for this study, all the tasks and work related to the study was performed remotely. Can you go to next slide, please? So the study site is located in Adirondacks, as we can see in figure 1, which is managed by Molpos Woodlands Group, which is a timberland investment organization based on Jackson, Mississippi. It has around 231,000 acres of timberland, mostly in central and western part of Adirondack Park, and comprise wide variety of forest stand, class, and species. In figure 1, the red outlined polygons are timberlands under management, and blue polygons are recently harvested areas within those timberlands. And we can also see the test site on top right of figure 1. So the blue polygon is the test site, and then the outline bigger study site is the timberland property for the test site. Can we go to the next slide, please? In United States, the National Agriculture Imagery Program regularly acquires high-resolution aerial imagery for USDA Farm Service Agency. For a given state, NAP imagery is acquired every 3 years during growing season. These imageries are all acquired within one growing season for the state, covering an extensive area in a short time. Hence, there is minimum chance between images. Minimum changes between the images. NAP data are 4-band multispectral imagery with spectral bands of near infrared, visible red, visible green, and visible blue band with 8-bit radiometric resolution and 0.6 meter spatial resolution. These imageries were downloaded from NAP Box Cloud Service, USDA Natural Resource Conservation Service, based on state and county Federal Information Processing Standard course. Then the imagery was maxed with the test site polygon using extract by max tool in ArcGIS Pro. Next slide, please. Thank you. Most recent, for this study, we also utilized LiDAR data. So most recent LiDAR data for study site was downloaded from New York State GIS Clearinghouse website. Raw LiDAR data were height normalized using digital terrain model, which is computed from LiDAR coverage separately, where its digital terrain model was computed on a fly such that an elevation value was imputed for each point in a raw LiDAR point cloud, and a complete digital terrain model surface was never created or saved. So the point was elevation was estimated using IDW or inverse distance weighted imputation using pre-classified ground and water region with 5 neighbors and power up to. LiDAR package was used in R to process and generate canopy height model of 1 meter resolution. As we can see, those canopy height model for the test site in figure number 3. Next slide, please. Thank you. Image segmentation was performed on NAP imagery prior to creating training data for image classification in ArcGIS Pro. So this was done using segmentation tool in ArcGIS Pro. Then training data was created on segmented NAP imagery. 5 different land cover classes were determined based on New York's ortho imagery from 2020 and visual inspection or interpretation on Google imagery. New York State ortho imagery are leaf of 1 feet imagery. About 50% of samples from each land cover category were created adopting 2011 National Land Cover Datasets training schema in ArcGIS Pro. Next slide, please. Thank you. So for image classification, we utilize random forest classification framework, which is used to classify the different land cover types. It's a non-parametric ensemble learning algorithm that tends to have a very high rate of accuracy and can handle large data sets, and is computationally less intensive than other classification algorithms. So if we look at the map over here for the classification work did work fine for classifying deciduous forest, but it didn't do very well with the conifer forest. If we go back, can we go to previous slide? Yeah, if we look at this 1 feet ortho imagery, there are dark spots which should be a conifer forest, but those conifers or evergreen forests were not properly classified in random forest using random forest classification. Next slide, please. And then also the water was not a water was classified well, but the shadows within the trees, underneath the trees, were also identified as water in the classification. This is an initial research, so I would be incorporating additional variables such as monthly imagery from PlanetScope platform and look into a tree leaf phenology to enhance classification and plan to classify in terms of individual tree species. So PlanetScope is a platform from Planet, which is an integrated airspace and data analytics company operating on largest commercial fleet of Earth observation satellite. So we can download satellite imagery for within a month. Like they have a data per month basis, and then we as a student or academic or someone from the academy can get a free subscription to download some satellite imagery from that platform. Can we go to next slide, please?
Sorry for interrupt. You only have 1 minute left.
Okay, thank you. So So furthermore, we utilize canopy height model derived from LiDAR dataset to investigate and detect individual trees based on local maxima field memory, where each local maxima corresponds to the individual tree top. Focal statistics tool was used to extract local maxima, and then to match the pixel value from the canopy height model and focal statistics, we use con tool in ArcGIS Pro. This con tool performs if statement on each of the input cells using raster calculator. Then the data sets were converted into point shape file, which indicates location of individual tree within the test sites. Then extract values to point tool was used with canopy height model raster and T-point point shape flights to estimate tree height. Can we go to next slide? So these are the three locations within the study test sites. So there were 13,103 located, and maximum height in the harvested area was 30 meter. Can we go to next slide?
Yes, you are wrong
Yeah.
all of time.
Yeah, so forest composition assessments can be done with utilizing this different open source imagery, and pre-processing does takes a lot of time, but we can get us comparable results from these open source remotely sensed data sets. So we don't have a field-based reference data sets, but that would have been very helpful to provide a validation and help in map accuracy assessment. Yeah, thank you.
Thank you. Are there any questions? Maybe could you quickly speak to the uncertainty aspect related to your work?
Sorry, I didn't get you.
The different aspects of uncertainty related to your work and the results that you got from the model that you implemented.
Yes, there are lots of uncertainty regarding the data sets and also the results I got. If we go back to the random forest classification, it didn't properly classify the land cover type. As we can see, like from the ortho image, there is 1 feet ortho imagery. There were lots of conifers in that study sites, but we couldn't classify that. It's possibly due to a very limited amount of training data sets, and also depending on what kind of data we downloaded, or the data downloaded, which season data we downloaded. So there is a lot of different uncertainty regarding that classification. And also regarding the tree height estimation and tree detection, also we do have uncertainty because we exactly don't know from the field what is the tree density per acre in that study site.
Okay, very